And welcome to our lecture on light emission, which is chapter 30. Okay, so we're going to talk about where light comes from. We'll talk about excitation. This means excitation of electrons within an atom. Emission spectra, how particular atoms have particular colors, in other words, wavelengths of light that are produced. How the process of incandescence works. How we can get spectra from absorption as well as emission. How the process of fluorescence works. Then phosphorescence. And then finally understanding the functionality at a basic level behind lamps and lasers. Okay, so it should be an interesting lecture. Okay, so first of all, we know already that every single electromagnetic wave, which is to say all light, is produced from the acceleration of charged particles. Okay, all light is from the acceleration of charged particles. Okay? We're going to specifically talk about light being emitted, which is to say where it comes from, in the context of electrons orbiting the nucleus of atoms. And this is a form of acceleration. The understanding of why it's a form of acceleration isn't immediately apparent. Because if the electron is, maybe this is an electron path in the picture, see? If the electron is circling the nucleus, that's the yellow bit, of the atom, then isn't it already accelerating? Isn't the process of essentially being in orbit, if that's what the electron is, isn't that a form of acceleration? Well, the answer would certainly be yes if it was in orbit. For example, Earth is accelerating around the sun. It is absolutely unequivocally accelerating. But the electron is not, because if the electron was accelerating while it is orbiting around the nucleus, then it would be emitting light based on our understanding of where electromagnetic waves come from. That's not the case. Okay? We'll talk about kind of how scientists arrived at that understanding of electron orbits in a later chapter when we talk about the Bohr model of the atom. Bohr, named after the scientist who got the Nobel Prize for his model, which was fairly inaccurate. But what we want to consider now is that there is a form of acceleration that the electron can undergo. And that's when it goes or transfers from one orbit to another. So if we think of these orbits shown in this diagram here as being shells, the transition between one shell or another is an acceleration. Okay? Again, that is not immediately apparent on our understanding of physics and classical mechanics at this point. We need quantum mechanics to have any understanding of that. But we need to take that at face value, that the only thing that's going to count as an acceleration for the charged particle, which is the electron in the case of the atom, is transitioning from one orbital shell to another. Okay? Now let's read the bullet points. Okay? So light emission is understood in terms of the familiar planetary model of the atom. Just as each element is characterized by the number of electrons that occupy the shells surrounding its atomic nucleus, each element also possesses its own characteristic pattern of electron shells or energy states. These states are found only at certain energies. We say they are discrete, like steps on a staircase. We call these discrete states quantum states. Quantum means broken into parts. Okay? As opposed to being continuous. Okay, so you can break it into chunks, parts, one stepping after the other. Okay? So that's the idea of the energy states of the atom. Notice that we said that every element is characterized by certain numbers of atoms that occupy shells. Okay? In a pattern that is unique to that element. So the pattern is unique to the element. All right, so when energy is imparted to an element, an electron may be boosted to a higher energy level. The atom is said to be excited. Okay, so it went to a higher level. Here's a great little cartoon. All right, it's got little faces on everything. So there's the nucleus. This is our atom. Okay, this is our atom at rest. Okay, it's in a rest state. The energy comes in. It excites the atom. Okay. And by the way, this is energy, but we can think of it as energy of a photon. Doesn't have to be. It could actually be another particle. It could be anything. It could be, say, a nucleus stripped of electrons. It could be some other particle, but it could also actually be a particle of light. But it comes in, it excites the atom. Look, it's all excited here. All right, that energy has to go somewhere. It manifests in the outermost orbit, becoming excited. And the dotted line shows where it used to be, where the orbit of the rest state of that particular electron of this particular atom used to be. All right, but after a while, we can see that the atom as a whole, represented by the face here, chills out, and when it does, it releases light. And it releases light of the same exact energy as the energy that got it excited. And there's no way around it. Those energies have to match up exactly. Otherwise, the atom never would have been excited in the first place. If there is no available matching energy for the atom, then you know what happens to this incoming energy, this here? It just passes by. Okay? If there's no way for that energy to be absorbed, then it won't be. And then we return to rest. Okay? So, excitation is what we've been talking about. Here's looking at it in a kind of a 2D, non-cartoonish way, or less cartoonish. Here's an electron in a certain state. It gets excited up to some higher state. The numbers don't mean anything. They're just showing that 2 is greater than 1. And then eventually, the electron is going to relax, and then it's going to release light in the form of a particle called a photon. Okay? Okay, so the frequency of the emitted photon is proportional to the energy level difference in the de-excitation. E, that's the energy level difference, okay? That would be this difference here. So the idea here would be E2 minus E1 equals E. So that exact amount of energy is equal to Planck's constant, 6.626 times 10 to the negative 34 joule seconds, times the frequency of the light, okay? And frequencies of light, visible light, is going to be in the range of 300 to 500 nanometers. A nano is 10 to the negative 9, okay? It's a billionth of a meter, okay? So that's it. That's the energy. Obviously, very small amounts of energy. You can tell right now, okay? Very, very small amounts of energy. And that's, okay? That's the idea. Oh, and this, excuse me, I want to correct something. So when I mentioned here, I said that I gave you the wavelength of the light, but this is the frequency. So if you wanted to relate the frequency to the wavelength, you would use the fact that the speed of light equals lambda times f. So then you can do a substitution where you replace f with the speed of light divided by lambda, like so. And you see in doing that, then frequencies are really big when the wavelengths are small. But the energies are still small, okay? But we're not multiplying two small numbers together. We're multiplying one small number, Planck's constant, h, by a fairly large number in the case of most light, f. And I guess, to be fair, by fairly large, I mean on the order of about 100 trillion. So I guess it's pretty big. And that's just the number of times that the wave cycles per second. And that corresponds to the wavelength and the fixed number, which is the speed of light, c. Okay? All right. That's it. And there's so much there. It's such a cornerstone idea because it lets us identify elements, but we'll talk about that. One question that you may be asking yourself is, this idea that the electron eventually relaxes back down to its unexcited state. How long does that take? Usually very little time. The time it takes to go from here to here is usually on the order of a billionth of a second. Okay? So it's going to be a very fast process, but there are exceptions. So which has less energy per photon? Red light, green light, blue light, or do they all have the same energy since they all travel at the same speed? Okay? Well, of course they don't all have the same energy because the energy is proportional to the frequency. which is to say that it's proportional to the wavelength. Okay? But look at the proportionality. It's not directly proportional to the wavelength, it's inversely proportional to the wavelength. So the greater the wavelength, the less energy. So as the wavelength goes up, the energy goes down. So longer wavelength light is lower energy light. Okay? And so which of these has the longest wavelength? Red. So red is the least energetic light. Okay? Energy is proportional to frequency, and it's inversely proportional to wavelength. Why do I keep talking about wavelength? Because that's the way that we probably or think about light most of the time. We think about its color, we think about its wavelength, we think about those easy to remember numbers 300 to 500, much more than we ever would be able to quickly remember the frequencies of even visible light. Okay? Excitation is the process in which, okay, we're talking about it, picture. What's the best answer? The electrons are boosted to higher energy levels in an atom. Okay? That's excitation. What's the opposite? Relaxation. The atom and its excited electrons relax back down to their ground state or relaxed state. Okay? Okay? So, if we have unique patterns of energy levels of electrons for any atom, then every atom has a fingerprint. Okay? And we can measure that fingerprint. So to measure fingerprint of an element. So hydrogen has a particular fingerprint. Helium has a particular fingerprint. Neon has a particular fingerprint. Why do I use the term fingerprint? Because fingerprints are unique. They identify people. Likewise, the emission fingerprints of elements identify that element, okay? Because of the pattern of excitation levels of their electrons. And the tool to do it is the spectroscope, one of the tools, an arrangement of a slit, a focusing lens, and a prism or diffraction grating. So you really got an option there because both are going to do the same thing. They're going to split up the wavelengths. To see the emission spectra of light from a glowing element, pass it through, focus the light, have it pass through a slit, okay? Pass through the slit, you then basically, you don't focus the light, you diverge the light. By diverging the light, then you're going to create 2 points of diffraction, and then those 2 points of diffraction are then going to allow for the red, yellow, and violet light to get positioned nicely and distinctly on a screen of some sort or a detection device, okay? Maybe a digital sensor. When an electron is at a higher energy level, the atom is excited and temporarily loses the acquired energy when it returns to the lower level and emits that radiated energy, right? There's that idea that we saw before, okay? So the spectral lines are the consequence of using the technique with the slit and lenses and the prism that we saw before, all right? And once we do that, once we get our spectral lines, we get an image of the slit on a screen using a spectroscope. Each component of color is focused at a different position according to frequency. Okay? So in this case, the red would be over here, the blue would be over here, the violet would be over there. Okay, see? Looks good, right? And see how that means that we have distinct patterns, distinct spectral lines, okay? Also called emission spectra, all right? Or you could say emission spectral lines, right? Those are kind of interchangeable terms. But the commonality is that word spectrum or spectral, okay? And look, you see like all these elements, mercury, zinc, cadmium, strontium, calcium, barium, all clearly shown. Some more complex than others, okay? Historically, the first one that was ever discovered were the spectral lines of hydrogen, all right? It's very orderly, more so than other elements. That's because it's such a simple element. It has one electron, okay? Successive lines get closer until the lines merge, okay? So basically the energy difference between them becomes smaller and smaller, okay? So this denotes a decreasing energy difference between each successive excitation level. The Swedish physicist, and mathematician Johannes Rydberg discovered that the sum of the frequencies of 2 lines often equals the frequency of a 3rd line, okay? And that was kind of starting to lay the groundwork for quantum mechanics, right? But we'll get there. We have a whole chapter where we talk about the historical saga of quantum mechanics, okay? And then there's a follow-up idea called the Ritz combination principle. It's a neat one. So Rydberg's discovery, called the Ritz combination principle, basically says that A plus B equals C. And this matches up nicely with that picture of the nested spherical shells that we saw in the opening slide, or the concentric circles that we saw a couple slides back, okay? Like the concentric circles that are shown partially here, for example. Because the idea then is if these represent energy states, such as the ground energy state and the second energy state and the third energy state, then the electron can get excited all the way up to the third one. So if our electron can jump up to the third energy state, then it can relax back down by jumping all the way back down to the ground state, or it might make an intermediate stop at the second energy state, okay? And if it does, then it's going to emit a different color, because B is a different energy and thus is a different color. And then if it did stop at the second energy state, then eventually it would then go all the way down to the ground and thus emit a third color, an even different color, and that one would correspond to the energy and the associated frequency, Planck's constant, wavelength, speed of light. They're all related, right? In fact, the equations are so simple, and I don't want you to forget them. Really, the only two equations we need to understand here, okay, as far as the light is concerned, it's the speed of light, it's frequency times wavelength, and the energy, including the energy difference between the electron levels, also equal to the energy difference of the photon. Okay, so here we'll say energy, electron, level, okay, all right, delta, electron delta level, right, because for difference, is equal to the energy of the photon, and then that's equal to HF. So see how these two formulas work so beautifully together? Okay. Okay. So most of what we know about atoms is gained by investigating what? How do we actually learn about atoms? Do we tear them apart? Do we dissect them with tweezers? No, of course not. Okay. So it's the light, right? It's a pretty indirect means of investigating atoms, but it's the best we got. Okay. So light emitted by atoms, their atomic spectra are considered to be their fingerprints. Okay, all right. So those are some of the basics, okay? Foreshadowing things to come in terms of our discussion of quantum mechanics, but also really explaining how light interacts with atoms, with individual atoms. Okay, all right, let's move on to another topic, incandescence. Incandescence, the frequency of radiation emitted by a hot body is proportional to the temperature of the hot body. There's a direct proportionality between frequency and temperature. Thus, a direct proportionality between wavelength and temperature. The radiation curve of brightness versus frequency for emitted light. So the vertical axis here is the brightness of the light. The horizontal axis is the frequency. And then we have two curves. We have a curve of a hot body. So it's a solid object that's hot, that has a temperature of 1000 degrees Celsius, and another hot body that has a temperature of 15 degrees Celsius. Notice that the hotter hot body has a greater peak intensity, but more interestingly, its peak intensity occurs at a different frequency and at a higher frequency. So we see that the color at which hot things glow tells us their temperature. There's a very reliable relationship between glowing solid objects, the color they glow at, and the temperature. It allows us to measure the temperature of solid glowing objects, which is pretty useful. It does not work for gases. It does require that the object is a solid. Okay, so incandescence. Isolated bells, this is explaining kind of the analogy of how we can understand it. Isolated bells ring with a distinct frequency, as atoms in a gas do. The sound from a box of bells crowded together is discordant, like light from an incandescent solid. Okay? So you're not hearing the distinct frequency anymore. You're hearing a bunch of sounds all together, creating a bunch of noise, but the noise has a pattern. Which lamp is more efficient for emitting light? An incandescent lamp, a fluorescent lamp, or they're both the same? Okay? This is just your common knowledge. Which one do you know to be more efficient? I bet you know the answer. It's fluorescent, of course. All right? And to understand fluorescent lamps, let's talk a bit about absorption. So an absorption spectra is the opposite of an emission spectra. Atoms in a gas absorb light of the same frequency they emit. That makes sense. We talked about that. Otherwise, the energy would just pass by the atom. A spectroscope can detect dark lines in an otherwise continuous spectrum. So a continuous spectrum is like that from an incandescent object, a hot body. Notice that there is not distinct peaks in this spectrum. There is instead, see, no distinct peaks. Instead, there is a nice continuous curve. That's the curve of a hot body. Okay? We call that a black body curve. That is absolutely different than the distinct spectral lines from a hot gas. Okay? What are objects that are incandescent? The sun is incandescent because it's such highly pressurized gas, it's behaving like a solid. Humans are incandescent. A red hot glowing piece of metal is incandescent. Okay? The filament in an incandescent light bulb is incandescent. Okay? So that's any solid glowing hot object. Now I say human, right? We glow at a temperature we can't see, but we do glow. We talked about that. Okay? So to follow up then, if you have one of those incandescent continuous spectrum sources of light, and then there is a not solid, but rather gas between the incandescent source and the screen, then you can observe the absorption by the gas that is between the incandescent source and the screen. Okay? Okay, so that's incandescence, very common, right? All solid objects produce incandescence. Now what about fluorescence? Okay? Well, fluorescence is a form of incandescence, but it has a particular characteristic to it. Okay? So fluorescence, first of all, many materials excited by ultraviolet light emit visible light upon de-excitation. Okay? The reason for that is because they're going to make multiple stops on their way back to being relaxed. Okay? So many substances undergo excitation when illuminated with ultraviolet light. Okay? So ultraviolet light might allow an electron that was down here in the ground state to go all the way up to, in this case, the first, second, third excited state. Okay? So a big jump. Why a big jump? Because ultraviolet light is high energy light. Okay? Now, that electron may not relax all the way back down. Okay? It is a somewhat random process. And so it's very likely then that the electron in its third excited state might then stop next at the second excited state. And in doing so, make a much smaller energy jump than it did during excitation. In other words, its relaxation energy jump corresponds to a lower frequency light, thus a longer wavelength light, and longer wavelength light would then correspond to visible light, because ultraviolet light is invisible because its wavelength is too short. So anything with a longer wavelength than ultraviolet light will be visible until, of course, it becomes too long again and it falls into the ultra-red spectrum. Okay? But for a while, anything longer than ultraviolet is visible. And so then there are many cases where ultraviolet excitation leads to visible emission. And that's what fluorescent is. Anytime someone says something is fluorescent, it's because it's being excited by high energy invisible light and then emitting through relaxation lower energy visible light. So this excitation and de-excitation process is like leaping up a small staircase in a single bound and then descending one step or two steps at a time rather than leaping all the way back down. Photons of lower frequencies are emitted, okay, during those more reasonable steps back down the staircase. Okay, so this leads to a fluorescent lamp. So in this case, a UV is emitted by an excited gas. Okay, that UV then strikes the phosphor material that emits white light. So though we often think of fluorescent objects as being the ones like we saw in the slide back here, those that maybe are considered, black light objects, because the black light is a energy source that includes, or a light bulb that includes invisible ultraviolet light. So That's kind of what comes to mind with fluorescence, but it turns out that fluorescent lamps, they are designed in a very clever way that instead of just emitting one particularly bright color, like glowing green, like something that's glowing under black light, they emit a bunch of bright colors that collectively show up as white, okay, with the way when they interact with the human eye. Okay, so that's the idea, but it's still the same principle as fluorescence, absorbing the ultraviolet light from the interior energy source, and then so the only thing you see on the exterior is the white light. So an atom that absorbs a photon can then emit, what do you think? One only at the same or lower energy, okay? Because it can definitely do the lower case. That's what fluorescence is after all, because then there will just be more photons coming. There'll be more intermediate steps. Make sense? Okay? Okay. So when excited, certain crystals, Now on to phosphorescence. Okay? Now phosphorescence is sometimes combined with fluorescence, to be fair. Sometimes you can have objects that are both fluorescent and phosphorescent. My children recently got a toy where there's a little ultraviolet pin. Okay, it kind of shows up in the purple. But that's just the tail end of the emission that you're seeing with the visible eye. But obviously, a lot of its energy that's emitting is invisible ultraviolet, and you're meant to then write on a specialized tablet, basically, just a screen that then will glow. Okay, and it will glow in the visible spectrum. It glows quite brightly, and it will continue to glow for a few seconds. Okay, so it doesn't once you turn off the pin, it continues to glow, or once you move the pin away, so you can write your name and it will sort of fade out as you write, almost like writing your name with a sparkler in the air. Okay, so what's happening there is a combination of fluorescence, turning the invisible light source from the pen into visible light that's being emitted by the screen, combined with phosphorescence, because the light doesn't just disappear right away. It stays glowing for a while. Okay? So, with that, let's read the bullet points and make sure we can understand what phosphorescence is. So when excited, certain crystals, as well as some large organic molecules, remain in a state of excitation for a prolonged period of time. That's at staying not just for nanoseconds, but a few seconds. Unlike what occurs in fluorescent materials, their electrons are boosted into higher orbits and become stuck. Okay? Which is why sometimes it does combine with fluorescence, because sometimes to get it just right, to find the engineers that designed the right materials that can be used for a toy like I was describing, well, they need to find the right energy level that an electron can get stuck in. Those energy levels are just particular combinations when we get down to the quantum mechanical background behind this. And often those combinations occur at the higher levels. So sometimes a higher energy light source is the trick to get it there. Okay? As a result, there is a time delay, because of the getting stuck part, between the process of excitation and de-excitation. Materials that exhibit this peculiar property are said to have phosphorescence, and some is much more pronounced than the toy I was describing. For example, there are some glow-in-the-dark materials that will glow for minutes or hours, right? Showing very, very pronounced phosphorescence. But they do tend to glow very faintly, so you can only actually see the glow in an otherwise dark surrounding, like a dark room. Okay? So continued. Atoms or molecules in these materials are excited by incident visible light. Okay? As I said, it doesn't have to be visible. Rather than de-excitating immediately, as fluorescent materials do, many of the atoms remain in a metastable state, a prolonged state of excitation, sometimes as long as several hours, although most de-excite rather quickly. If the source of excitation is removed, for instance, if the lights are put out, an afterglow occurs, while millions of atoms spontaneously undergo gradual de-excitation. And it's a random process. Okay, this is a stochastic phenomenon. Some will relax right away, but there's a certain likelihood that a number of atoms in the population of millions upon millions of atoms will remain excited. Many living creatures, from bacteria to fireflies, and larger animals such as jellyfish, chemically excite molecules in their bodies that emit light. Such living things have bioluminescence. See? And really that excitation is that the chemical excitation is always going to be combined in the cases that we notice as bioluminescence with those metastable states, because otherwise the chemical reaction rate couldn't keep up to really glow. There needs to be an afterglow. Because if the excitation was as quick as it is in the case of emission from a gas, then the chemical would have to be continually producing at a time scale of nanoseconds. And there's not a chemical process happening at that scale. Instead, the chemical process can happen at the scale of seconds, or at best fractions of a second, and then that afterglow makes the glowing appear continuous. Okay? All right, on to lamps. So we talked about incandescent, right? Hot bodies, black body, continuous spectra. Okay, so now let's talk about an incandescent lamp. So a glass enclosure with a filament of tungsten, for example, through which an electric current is passed. The hot filament emits a continuous spectrum, mostly in the infrared, while a small part is visible. Essentially, if we were to look at the brightness, okay, and over here we have the frequency. Then we have a curve with a peak frequency, okay, and that peak frequency corresponds to infrared light, okay. So the frequency is such that it's invisible. It's just heat. And then so the visible part would only start over here, right, where there's already less intensity. Why do I bring that up? Well, because that really is a testament to how inherently inefficient incandescent lights are, unless you're using them to heat things, because they're more of a heater with an invisible peak than a light source, because we're getting the visible part over on the tail. That's why more modern lights, whether they're fluorescent or LED, have become so much more efficient at producing light and less wasted heat, because we can fine-tune that frequency and get the visible frequency to actually be the peak of the hot body incandescent curve, rather than the peak to be invisible. Okay, so the glass enclosure prevents oxygen in the air from reaching the filament to prevent burning up by oxidation. Okay, so it's important to be surrounded by a vacuum. The argon gas with a small amount of halogen is added to slow the evaporation of the tungsten, because it is burning off. And the efficiency in an incandescent light bulb is about 10%. And that efficiency is turning basically the electrical energy of the circuit into visible light. Okay, the rest of it goes to heat. Okay, all right. We talked about the fluorescent lamp already. Okay, compact fluorescent lamps, CFL. They miniaturize a fluorescent tube wrapped into a coil and outfit it with the same kind of plug a common incandescent lamp has, and you have a compact fluorescent lamp. Okay, this was a big deal 10 years ago. Now we've actually mostly moved on to LEDs. CFLs are more efficient than incandescent lamps, putting out about 4 times more light for the same power and input. Okay, right? And to be fair, when we say 4 times more light, we mean visible light, because they both produce a bunch of light. It's just that the incandescent is producing invisible light, which we call heat. Okay? A downside to the CFL is its mercury content, which possesses an environmental disposal problem. All right? LEDs, here's a nice LED. Okay? A diode and a 2-terminal electrode device that permits a flow of charge in only one direction. One kind of diode design is the reverse of a photocell, in that an impressed voltage stimulates the emission of light. This is a light-emitting diode. Okay? And so you can actually create light bulbs that way. So a semiconductor layer containing, this is just continuing the idea of how the LED works. A semiconductor layer, these are semiconductor, neither a conductor nor a insulator, containing free electrons, is deposited onto the surface of another semiconductor that contains energy holes that can accept the free electrons. An electrical barrier at the boundary of these two materials blocks electron flow. When an external voltage is applied, the barrier is overcome, okay, because it's not infinite, and the energetic electrons cross over and drop into the energy holes. In this way, similar to de-excitation in an atom, the dropped electrons lose potential energy that is converted into light, and then you can match the depth of the hole to a particular color. Okay? All right, pretty neat idea around LEDs, huh? Last idea of the chapter, lasers. Okay? So a laser, okay, well, a laser is not this. It is not incoherent light. Instead, we'll discuss how it is coherent light. But by the way, incoherent light is many frequencies and out of phase. Okay, so we got all colors, and the peaks and troughs of these different waves don't line up. Okay, so incoherent is neither in phase nor all the same color. Okay, a laser, on the other hand, is monochromatic and and it is out of phase. Okay, excuse me, not there yet. So the laser isn't, but monochromatic light that is out of phase is shown in this picture. Okay, so let me make sure I'm clear on that because I misspoke just a moment ago. This picture here is showing incoherent light. This picture is showing monochromatic light, so all one frequency now, but it's out of phase. Okay, now we have coherent light, okay, and it's in phase. Okay, so coherent light of identical frequencies in phase. And so in fact, when we say coherent light, we mean identical frequency and in phase. Okay, so a laser is a device that produces a beam of, you guessed it, coherent light. Many types and many ranges of light, all right? Not a source of energy, as it is sometimes called, okay? The laser consists of a narrow Pyrex tube that contains a low-pressure gas mixture consisting of 85% helium, okay, which are the small black dots, and 15% neon, the large colored dots, okay? And I shouldn't say a laser, I should say the laser consists of a narrow Pyrex tube. Why? Because we're talking about a rather old-fashioned but wonderful demonstration of what a laser is. This concept has been refined many times, different materials have been used, but some of the original lasers were a mixture of helium and neon, and it definitely shows the principle behind them. Okay? So when a high voltage current zaps through that tube, that one with the helium and nitrogen in it, it excites both the helium and the neon. Okay, so helium and neon. I think I misspoke a second ago. Helium and neon. Okay, so those atoms are excited to their usual higher states, and they immediately undergo de-excitation. Okay, except for one state in the helium that is characterized by a prolonged delay before de-excitation, a metastable state. Okay, so now the usefulness of the helium is becoming apparent. That helium has a particular metastable state, just due to basically certain combinations of states are inherently metastable, okay? It all has to do with the angular momentum and conservation of energy of all these different states and the many, many different states that can exist, okay? So since the state is relatively stable, a sizable population of excited helium is built up, okay? So when you continue to run the current, you get more and more helium that just remains excited, okay? So these atoms wander about in the tube and act as an energy source for the neon, which has an otherwise hard-to-come-by metastable state very close to the energy of the excited helium. Okay, so you can see you have that the design of these lasers, you have to know a lot about the atoms. You have to know that the helium has a more accessible metastable state. The neon was a natural choice to combine with the helium because it has a similar energy metastable state, but one that isn't as easily reached, okay? But now having a population of the hydrogen that can bump into the neon increases the likelihood of the neon metastable state being reached. So when the excited helium atoms collide with the neon atoms in their lowest energy state, the ground state, which most of them are going to be in because the current that is still running through the gas is exciting the neon, but the neon is immediately relaxing. Okay, so basically, functionally, when they are able to be collided with by the metastable excited helium, then they're all going to be in their ground state. The helium gives up its energy during the collision to the neon, which is boosted to its metastable state. Okay, we'll see in the next figure as red open circles. The process continues, and the population of excited neon atoms soon outnumbers the neon atoms in a lower energy state. Okay, we still have some metastable hydrogen, fewer now because most of them have given up their energy, and we have quite a few of the metastable neon. This inverted population is in fact waiting to radiate its energy. Okay, we called it an inverted population because we've gone from the easily achieved metastable state of the helium to the difficult to achieve metastable state of the neon because of them both coexisting in a chamber, forced to collide with each other, and because of the relative numbers of each. Okay? And so it's an inverted population. You have more of the harder to achieve state. That's why we call it inverted. Some neon atoms eventually, because they won't stay excited forever, de-excite and radiate red photons in the tube. When this radiant energy passes other excited neon atoms, the later are stimulated into emitting the photons. All right? So that's the thing about a metastable state. Okay? Is that it is somewhat of a unstable situation because it will remain, again, stochastically, and when I say stochastically, I mean probabilistically stable, probabilistically just resting there in that state with a certain likelihood of relaxing. But, if energy passes by that exactly matches that state because it came from an identical nearby atom, then it will always cause the metastable state to collapse. It will cause the photon to get emitted. That's called stimulated emission. Okay? And that is so fascinating because stimulated emission always achieves the other neon atom to emit light that is exactly in phase with the light that stimulated the emission. Okay? Which is the radiant energy that stimulated the emission. Okay? So the photons pass out of the tube in irregular directions, giving it a red glow. Okay? But this is a lot of coherent light. See? Coherent light. So the photons moving parallel to the axis of the tube are reflected from specially coated parallel mirrors at the ends of the tube. Okay? So the photons are absolutely not going to be directed at this stage of our explanation of the laser. But the mirrors at either end are going to mean that over time, the waves that are bouncing back and forth from the mirrors will become dominant over the random direction mirrors, or random direction photons. Because the random direction photons are simply going to hit the sides, many of them getting absorbed into the sides of the laser. Okay? But the ones bouncing off the mirrors will continue to bounce off. The photons flash to and fro between the mirrors, becoming amplified with each pass. So now if you look, you find very few photons with vertical components, like this one here, and more of them just going back and forth, okay, stimulating the emission of more coherent light of the identical color. So some photons leak out of one of the mirrors, which is only partially reflecting. This makes up the laser beam. Okay? So you could literally have a hole in the mirror, so there's a certain a chance of the photons passing through a hole, or just make it, as discussed here, partially reflective, so there's always a certain amount coming out. Okay? And that's your laser. I thought there was one more slide, but that's your laser, your coherent unidirectional beam of light. Okay? And by coherent, we mean that it's in phase and it's monochromatic. Okay? And to get there, what did we need? We needed 2 metastable states. Okay? We needed one to be harder to achieve than the other, and this meant that we ended up with population inversion. Okay? Just because one of the metastable states was harder to achieve than the other. The population inversion then allowed for the potential to lead to stimulated emission. Because only stimulated emission can explain the in-phase part, which we need if we want the light to be a laser light. which is such useful, distinct light compared to other light sources. All right? Pretty neat stuff. You can really see how probably the first experiments to just address some of these issues and kind of discover how light works in these different states would have led to the discovery of creating this type of light, the laser, and then how it has stuck around with us for so many decades since, almost a century since, because it has been proven to be so useful in so many applications. Okay? All right. Well, I hope this lecture on the emission of light and some examples of emitted light has been both interesting and informative. Thank you so much for watching.